So, good evening, everybody. So, it's really my pleasure to introduce this lecture by Professor Kolmanovsky. So, Professor Kolmanovsky is a professor of the aerospace engineering department of University of Michigan, Ann Arbor. And when I proposed him to apply for this chair, I was really interested in the fact that he has a very particular profile, because he's someone who had important contribution from the theoretical viewpoint during his PhD. And after that, he decided to go in the industry for a long time. So he was in Ford Motors for almost 15 years, if I remember well, where he kept, while being in the industry, publishing, proposing innovative solutions, both technical and from theoretical viewpoint. And then after 15 years, he came back to the academia, where he is now a very well-known person in our field. So he serves various organizations in various capacity, notably as associate and senior editor of various journals. He has won several prizes. And I think it's particularly important to remark that personally for me is an example of a control engineer that is able to have at the very same time a practical regard on things, but a very fundamental and rigorous methodology on how he does things. So it's my pleasure to introduce Ilya Kolmanovsky for his lecture.
Thank you very much, Professor Garoni, for a very kind introduction. It's my real pleasure to be here and an honor to present the first of this lecture series, where I'd like to speak a little bit about emerging opportunities for automotive engines, powertrains, and vehicles, connectivity, computing, control, and autonomy. And I inserted the word control into the title of my talk, which wasn't there originally. It was an omission, but it surely should be there. Just so that you a little bit can relate to my background in understanding some of my remarks, I got my PhD in 95 at the University of Michigan, Department of Aerospace Engineering. Then I moved to Ford Research and Advanced Engineering, worked on engines and powertrains for close to 15 years. And then I pretty much came back as a faculty to the same department. And so extent of my career, I usually summarize as moving one floor up in the same building. I was a student before. But this particular talk is about cars and automotive vehicles. And it's a broad talk, so I'll touch on a number of broad topics, but also describe some of my own research as well. So if you think about some of the most successful automotive products, especially early on, then one of them is Ford Model T, and have been about 15 million vehicles sold. And in the early 20th century, it defined desirable, affordable automobile enabled by new technologies in mechanics, materials, and manufacturing. And so a few years ago, now close to 15 or more than 15 years ago, a few of my colleagues and I, we started to think what would be sort of an analog in the 21st century Model T. And fairly quickly we realized that it's probably not just about the hardware, what engine or what powertrain such vehicles would have, but it's more than that, and it's more about control, computing, and communications, and the underlying software. And this will be the technologies that will shape the personal mobility experience of the 21st century. The Model T was self-contained, but as far as 21st century vehicles, they really will be defined by the external reach of wireless communication technologies, and automobile in some sense will be only one component in a large intelligent transportation infrastructure. And, as far as we can tell, 15, 20 years later, this is happening. Now, the bit of statistics about automotive world, it's actually a fairly large enterprise. There is about 100 million cars per year which are being produced worldwide. This is pre-COVID. Numbers for the last few years may have been different. More than 1.5 5 billion cars are in use worldwide. Transportation in the US, it's about a third of energy consumption. And some of the trends is growing powertrain electrification, move towards more electric vehicles, proliferation of ADAS, advanced driver assistance systems, and automated driving functions. And this photos show Ford Lightning, which is electric, fully electric powertrain being produced. So clearly, one of the trends has been towards electric vehicles, but what we see currently on the market, this is not the first electric vehicle, and in fact, the first production program goes to somewhere around 1900 by Porsche, and that vehicle had a lead-acid battery and a fairly reasonable operating range of 50 kilometers for that time. Now, if we move fast forward to present time, or more towards the present time, another notable attempt was in the 90s, and there was EV1, Electric Vehicle 1, by General Motors, and it had 170 kilometers range with nickel metal hydride batteries, which was pretty good for that time. But as far as the product itself, it was pulled off the market, and primarily because there was no customer acceptance at the time. People were not buying electric vehicles at the time, and of course that started to change more recently. And of course we recognize Tesla, but other manufacturers as well. And currently, the new vehicle sales, perhaps about 10% of them or so, would be electric vehicles. So this is one of the Ford products, Ford Mach-E, and that has a 640 kilometers range with lithium-ion batteries. But what's also different, besides batteries about it, is that if you look closely, well, there is a 15.5-inch touchscreen, which is nice to have. But more importantly, there is a cloud-connected navigation. And so Ford electric vehicles are all connected to the cloud. So these are connected vehicles. And the point that I'll try to make is that makes a fundamental difference in being able to accept such vehicles by the general public. So one of the key issues in accepting electric vehicles is the so-called range anxiety. So about 40% of customers concerned about electric vehicle range. Basically, the car can run out of charge in the middle of the road, and because the density of charging stations is not high at the moment, but also charging takes time, that's a concern. Furthermore, if some of the stations can have issues, for example, blocked or broken chargers, and if you look at driving in cold weather conditions, which happens in Michigan, for instance, the range can be reduced quite a bit. For example, by 30% in the case of Mach-E. So this is a type of application where cloud connectivity and generally being aware of information is really a technology that enables these vehicles. What happens is that you can learn energy consumption models for individual vehicles on the cloud, estimate the range and predict the range to be able to alleviate customer range anxiety, provide range extension advisory, as well as provide routing and recharging advisory. And in case of Ford's working on a number of features, such as Ford Intelligent Range that implements this type of functionality. So our picture basically changes. If before we had an individual vehicle, and we were confined to this vehicle, now the vehicle is just a node in a larger information architecture. We have a cloud. The cloud can have access to traffic data, weather data, as well as driving data. In principle, there is a computational unlimited resource on the cloud that you can use for model identification, optimization of energy management and eco routing, and even develop a bank of control policies that are specific to a given driving location, for example, high altitude versus normal altitude, and have those policies available on demand. A bit more of statistics or some of the interesting information. So the cloud computing at the moment is viewed as one of 5 most important areas of technology. And some of the industry sectors that will be most impacted in 2023 is actually automotive and transportation. So this is quite relevant. Just wanted to show this slide very quickly that connectivity is not just connectivity to the cloud, but also vehicles can be connected to infrastructure in various ways, for example, to traffic lights, to other vehicles. There is a short range communication, DSRC, and then there is a cellular networks that provide ability to connect to cloud and to internet. So now I'd like to say a little bit about some of the work by my students, collaborators in this area, in a sense how we try to explore the connectivity and information available for such connectivity to enable new vehicle functions. So this is something that we call cooperative road anomaly detection. And if you have been to Michigan, you know that the roads in Michigan, they have quite a few potholes. And part of it is winter and other reasons. But you see potholes like this. There are quite a few of them. And using vehicle sensors, one of the things you can do is to build a detector that detects whether you hit the pothole or not. And this particular detector, it's an estimator. Turns out that we don't just use something like a Kalman filter, which is more or less standard in these applications, but we use something called jump diffusion process estimator, where the road input is represented as a sum of a Wiener process and Poisson process. And Poisson process in probability theory, it's something that's quite effective in modeling rare but important events, such as hitting the potholes. And using the jump diffusion estimation provides better estimation accuracy in being able to detect the potholes. So now we have these vehicles driving around and they hit the potholes. And what we can then do is to aggregate the reports, the GPS coordinates where the pothole is hit on the cloud. Now, of course, there is a noise, so reports are not exact. And so what we have to do is to use some kind of evolving clusters to be able to aggregate the reports into the potholes. And as the potholes can be repaired and disappear, so once you start not receiving the reports, some of these clusters become, or the weights of these clusters become smaller and they eventually disappear. So it's really a model where we treat of the potholes by these evolving clusters as we receive the data. Now, once you're able to learn this road anomaly information, you can convert them into route planning systems. For instance, you might say that, well, I don't want to drive along the roads with many potholes. I'd like to have more comfortable ride. So I could create a cost function that weighs the time, of travel, perhaps the energy or fuel consumption, and then the comfort index. And you can optimize this to decide on the route to follow. And if you're willing to spend more time driving and you increase the weighting on the comfort, you could come up with different routes that are more comfortable to drive. So this is one of the uses. Here's another opportunity, what we call safety-based route planning. The idea is that there is quite a bit of data on different accidents along different roads. And we can data mine the database of those accidents and create something called road risk index. So given a particular road segment, we can estimate how likely is it that an accident might occur over that road segment. Now, of course, it's important to also add real-time factors. For example, the weather. A piece of road might be covered by snow. or a time of day and day of the week. And so you could create a model for the road risk index of this kind, and then you can integrate it into route planning system. And so here's an example where we might plan a faster route of about 42 minutes. But if we increase the weighting on safety, we might actually avoid certain areas, and it will take us 2 minutes longer, but we will drive a bit differently. Now, if we have weather report that says that some of the roads are covered by the snow, the route might also be modified. In fact, we go back to the original route. And if we drive at a particular time of day, for example, late at night, 1 a.m. Saturday, the route might change again, because at 1 a.m. Saturday, there is a lot of tired drivers and the people on the roads. It's also perhaps the time where people, some of the bars close, and maybe some of the people get on the road not in a good state. So we might avoid some of these areas. So hopefully this gives an idea of how this type of systems can be created. This is another possibility of using connectivity for cloud-connected vehicle diagnostics, monitoring and prognostics, as well as condition-based maintenance. Here we are talking about, for example, predicting when you have to replace brake pads or tires for the vehicle, as well as other components. And so if you look from a broader perspective on a range of these problems, typically what you have is that you have some parameters that are local, that is specific to the individual vehicle, and other parameters that are global, that are common to all vehicles. For example, tire pressure would be individual or local to each vehicle, but something like drag coefficient would be typically common to all vehicles. Or for example, the rate of brake change wear versus the kinetic energy dissipated in the brakes could also be viewed as a global parameter. So you have to somehow estimate both local and global parameters, and you have to reach the consensus on global parameters on the cloud, because the values of the global parameters have to be ultimately the same. So how to do this? Well, it turns out that at a fundamental level, this problem is a recursive least squares problem, essentially least squares problem to find the values of the parameters. And if you look at some of the optimization algorithms to solve this problem, in particular something called alternating direction method of multipliers, and you write down the structure of the updates, you could sort of see which ones of them you could perform at the vehicle level and which ones of them you can perform on a cloud. Now, you would think on the cloud, you would just do simple averaging, right? You would just average estimates at the individual vehicle level, but it's not as simple because the confidence at the individual vehicle level in these estimates may be different. So ADMM pretty much tells you what information you have to transmit and which updates can be performed where. It's possible to enforce constraints if you know that parameter ranges lie in certain intervals, as well as if you have several classes of vehicles sharing the parameter, the global parameter. You could also figure out on the fly what these classes are and what the values of the parameter are. So this is quite useful for diagnostics and prognostics. Now, this has been, in a way, an area of special interest, which is what can you do if you have access to weather, either current weather or weather forecasts. And we started some of this work back in 2009, if not earlier. And the idea is that you could access the weather service from the vehicle over the internet and get some information. How can you use this information? Well, if you can read the humidity, that can be fairly useful because there is no humidity sensor on a vehicle. And you can use it to adjust engine spark timing, as well as improve air-to-fuel ratio sensor accuracy. And that's good because it can improve fuel efficiency a bit, as well as reduce emissions a bit as well. Ambient pressure is something that you can use to save the cost. You can remove one of the sensors in the vehicle, barometric pressure sensor, or you can use it for its diagnostics. Now, the other thing that you can do is to access wind speed and wind direction. But at the time that we looked at it, we could read it in a car, but these measurements were only at the location of the vehicle, over the weather station. So they were not at the location of the vehicle. And so we had to extrapolate to the location of the vehicle, and that was a very hard problem to do this extrapolation. But the situation has changed, and in more recent years, some of the weather services are becoming increasingly sophisticated, and they do this extrapolation for you. So now you can literally query the weather service with GPS coordinates and time, and it will give you either current or predicted information, for example, about wind speed and wind direction. And so that can be useful. For instance, you can try to correct the range estimate or range forecast, accounting for wind speed and direction. And so the idea here would be to, if you have a route and you learn nominal energy consumption models on a cloud, and you also can read wind speed and direction, you can define certain correction factors that you can also learn in principle and correct the range estimate. Now, this is not necessarily straightforward to do because there is many uncertainties in this forecast. In particular, you can't reliably predict how the vehicle is going to accelerate in the future. So predicting the vehicle trace, it's actually quite involved. But certainly, if you have strong tailwind or strong headwind, those type of corrections can be quite useful. And then you can implement this in terms of the routing, various type of routing schemes. For example, decide on route to follow, vehicle speed along each segment, and charging time at charging stations. We use dynamic programming to solve this type of problems, but there is a variety of other techniques that can be used. So I hope that it's fairly clear there's many opportunities to implement new vehicle functions by exploiting the cloud. What about connectivity to, for example, traffic lights or connectivity to other infrastructure? So it turns out that you can also do a few things here at powertrain level. And this is an example that where we looked at the vehicle with turbocharged gasoline engine and dual clutch transmission. And so the dilemma here is that you're trying to start from idle and you're trying to accelerate the vehicle as fast as possible. So you are in a Fiesta next to Ferrari and you try to accelerate faster than Ferrari, roughly speaking. So what can you do? So the dilemma here is when to engage the clutch. So if you engage the clutch early, then the engine has to accelerate and drag full vehicle inertia with it, right? So that's going to be slow. But if you delay the clutch engagement, then what's going to happen is that the engine will accelerate fast and go to higher speed from which you can perform the engagement. But the trouble is that during this period, basically the vehicle doesn't respond, so you have hesitation. So how can communication help? Well, if you have a preview that the light is going to turn green and you don't have another vehicle up front, what you can do is that you can increase the engine speed. So you could go to higher engine speed before the actual launch event starts. Furthermore, you can preposition the other engine actuators for faster launch, and in fact, you can try to optimize their trajectory during launch. And it turns out that just with a preview, just through the communication, you can get with 7% higher final vehicle speed. But then if you can preposition and control engine actuators during launch, you get, together with a clutch, of course, you get about 25% higher vehicle speed. So that's interesting. The other opportunity is if you're operating in automated parking scenario or in automated driving corridors, you have infrastructure-based sensors. So not all sensors have to be on a vehicle. Some sensors can be integrated with the infrastructure. For example, if you are within a parking lot, you could have cameras, and you can fuse vehicle measurements together with infrastructure measurements to create estimates that you need and localize your vehicle. Here we do some experimentation with estimation algorithms that we use on mobile robots, but we have simulation results for vehicles doing automated parking. In this setting, the specific classes of algorithms that we exploited for estimation, they're not conventional statistical Kalman filter based, but we use deterministic algorithms called set membership estimation. So these are deterministic algorithms, and they have certain advantages for this kind of applications. So hopefully this gave a few examples how we can exploit the connectivity. What I'd like to do next is to talk a bit about computing and computations. So at the time when I was probably 5 years since starting at Ford, that was about year 2000, we had to work with very limited onboard computing power. So if you look at a typical computer on board, a powertrain control module, the clock speed was about something like 30 megahertz, and there was about 40 kilobytes of RAM. There was 1 megabyte of ROM. The processor at the time already was 32-bit floating point, and that was enough to do a basic control of the engine and transmission and meet emission regulations. But of course, you couldn't be you were limited in what you can do with advanced algorithms that require some computing power. So one of the things that has been happening more recently is that there has been a growth in onboard computing power. Certainly, the powertrain control module clock speed and memory have increased, perhaps in order of magnitude compared to those times. The multi-core processors are being used. The vehicle has several dozens of modules, several dozens of processors interconnected over several vehicle networks. In fact, if you look at infotainment system alone, that packs a very significant computing power. And then if you go to systems that implement advanced driver assistance as well as automated driving, people often characterize them as computer on wheels, mobile computing platforms. So you have significantly more computing power available. And that creates opportunities for implementation of more advanced algorithms that are developed in the literature. In fact, one of interesting opportunities have been the implementation of model predictive control, and that's an area of research for my group, as well as I think Professor Garonia's group here at ULB. To give you a basic idea of what happens in model predictive control is that you use a model to predict the response into the future. So you plan your trajectory into the future, and then you use an optimization algorithm to optimize this trajectory with respect to control actions that you can take. So it's essentially a trajectory optimization approach into the future. But you do a little bit more than that because you only apply an initial portion of the trajectory, and then you repeat this process. So you look further into the future over the same horizon, you compute the new trajectory, apply the first move, and so on and so forth. And you always update your model using most recent sensor measurements. So it's a form of feedback. It's a form of feedback that's generated through the optimization. But of course, performing trajectory optimization on board, it's complicated, takes some computing power. If we solve optimization problems, we of course know that. And so this growing computing power helps. This is another way to think about model predictive control. Sometimes people compare it to playing chess because optimizing over a future horizon of several moves gives you a better strategy. The best current control action would depend on what one plans to do later. And of course, when new measurements are available, one sees what the opponent does in terms of the moves. You can replan that trajectory of moves into the future. So model predictive control has a long history in control applications. It actually emerged in late 60s in academia and in late 70s in industry, but not in automotive industry. It emerged in chemical process industry and has been very successful. There has been also extensive research on theoretical and computational aspects of model predictive control in the academic community. And over the last 20 years, there has been increasing interest also in automotive industry that's enabled by growth in computing power. And there has been recent successes in terms of actual production implementation by General Motors, and they have implemented it for engine control and transmission control. There's a number of other manufacturers that are pursuing this type of methods for their applications. Now, I'd like to tell you a little bit about some of the work that we have done applying the MPC, and this is in the area of to reduce engine emissions. And here we've been working on diesel engines. Diesel engines were once popular for passenger cars, but they're being phased out. Nevertheless, they're not dead yet because larger vehicles, commercial heavy vehicles in particular, they predominantly use diesels, and so the emission reduction is important. Also, some of the efficient airplanes use diesel engines, as it turns out. The solution that we developed for diesel engine emission reduction involved not just one model predictive controller, but actually there were three of them. There were two in the inner loop, which we call air pass. So they were controlling air pass, the gas flows within the engine, feed forward and feedback. And then there was a supervisory MPC in the outer loop that would generate commands or set points to this inner loop MPC. Now, why such complicated architecture? Well, there are some reasons that this is very helpful to enable better control of engine in transients. So this allows to have better control of engines in transients. And in particular, you are able to reinstitute exhaust gas recirculation into the engine faster after an acceleration event that you can do with conventional methods. And this is very helpful in terms of being able to reduce the peaks in oxides of nitrogen emissions during the transients. And so this is what MPC allowed to do, is to have better controlled transients. We were fairly pleased with the results. And if we look at the computational times, we've been able to run all of these three MPC controllers under 1 millisecond. This is an D-Space Rapid prototyping system, but so the execution is fairly fast after optimization steps that we took. Okay, so now I'd like to turn to the third topic in this presentation, which is autonomy and autonomous vehicles, automated driving. And here we refer to vehicles that use advanced sensors, camera, radar, LiDAR, GPS, IMU, use advanced perception systems to understand what happens with them and also with the traffic around them, as well as pedestrians. Planning, both strategic and tactical planning in terms of route, path, and the actual trajectory, which is then commanded to vehicle controls and powertrain controls. By the way, there is a possibility to integrate connectivity and automation together. In this case, we have a connected automated vehicle, but you have other variants where you only have a connected human-driven vehicle or automated vehicle without connectivity. Generally, you have 5 levels of automation, from level 0 automation, which is no automation, to level 5 full automation, and then there's everything in between. Automated vehicles, of course, have significant societal promise, particularly enabling people who are not able to drive to have an option for transportation. And there are a number of scenarios which are attractive in terms of level 4 automation. For instance, low-speed shuttle or freight transportation. There have been some successes, of course, with level 2 and some level 3 vehicles. But for high level of automation, perhaps there is a growing realization that there remain quite a number of challenges. But there are quite a number of functions that connected and automated vehicles allow, and in particular in area of safety, environment, and mobility. And I'd like to mention that some of the challenges in enabling high level of automation actually lies in the area of correctly accounting for human interactions. If you try to deploy model predictive control in this type of settings, you need to be able to predict the trajectory not just of your vehicle, but also of vehicles around you. And in some of the scenarios, you have to interact with other vehicles. For example, here you're trying to force merge, and you have to kind of nudge your way in. And this is an example that the vehicle is not able to do that. And you could imagine scenarios at the intersection where, again, it's very important to understand what happens in terms of the interactions and make correct decisions in this type of scenarios. Now, at my next lecture, I will discuss this a bit more in terms of type of solutions that we are developing. But essentially, to model some of these interactions, we use models based on game theory. We use Bayesian inference to try to understand which model each of the surrounding vehicles follow, and then we use something called stochastic model predictive control, scenario-based model predictive control, to then optimize our decisions. We have also looked quite a bit at, I would say, maybe not quite a bit, at problems in integrating perception, learning, and control, which is very important for this type of applications. This is an example where we looked at end-to-end learning, that we literally look at camera images, and we essentially do the whole chain towards the driving actions using a combination of machine learning and reinforcement learning type of techniques. How much time do I have? Just to, I know that. Okay, very good. So what I'd like to do then is, for today's talk, I'd like to talk a little bit about some of the opportunities in automated vehicle and what we call eco-driving. And essentially the idea is that through automation achieve some energy consumption reduction benefits or fuel reduction benefits. This is a survey article that projects about something in order of 20% benefit in terms of eco-driving. There are multiple ways how you can enable this savings, but before I talk about some of the work that we've done in this area, I want to just mention that there are also energy costs of automated vehicles, because if you look at some of the advanced sensors and as well as the computers on board, it actually takes electrical power to drive them. And some of the estimates that have been done in the past, it could be up to 5 kilowatt to actually drive all of this. And so the fuel economy benefits of connected and automated vehicles could be significantly offset by these loads and energy losses, and in particular, the ones needed to cool advanced electronics and onboard computers. So one has to look at all the trade-offs involved. Now, ARPA-E, and ARPA-E, it's a federal agency in the U.S. which looks after energy innovations. Had a program called NextCar that starts at about 2017. And the goal of the program is to achieve additional 20% reduction in energy consumption for future connected and automated vehicles. And there have been a number of projects that have been selected for funding, including the project that I participated in on the University of Michigan side, which has to do with integrated vehicle power and thermal management. And the interesting aspect here that I think was appealing to the sponsors here is that we've looked at thermal management aspects for automated driving. Now, what did we do when we started on the project? Well, one of the first things we did was to purchase a vehicle, and this was a Toyota Prius that we bought these project funds, and we started to drive it around and see what happens with energy consumption or fuel consumption in particular. It's a hybrid electric vehicle. If we turn the air conditioning on and off. And as you can see, if you turn the air conditioning on, there is a quite significant drop in fuel economy. And a similar situation happens for heating. And so you look at these numbers and they're quite large. And so you think that there is a significant benefit. But turns out the story is very complicated because, well, these numbers are large, but you can only at best get a fraction of that benefit because you can't just tell people don't turn AC or just buy a warm coat and don't turn on the heating. That's not an option. So you still have to maintain cabin temperature, and you also have to maintain the other component that's very important to manage the temperature of is a battery, of course. So you have to maintain those. And so certainly it's not that you're going to get 50% improvement here for sure. Now, yeah.
How is it possible? You spend half of the consumption for the air conditioning?
Well, this is for specific drives, of course. I wouldn't say that it's a typical, but for air conditioning, 30 to 40 to 50%. I mean, you could see this type of numbers. It's actually quite. Now this is full power on, full AC on, right? So you may not. This kind of extreme what you can expect. But bottom line is that if you don't use AC or you don't use, especially in electric vehicle, if you don't use the heating, you would of course save the energy and extend the range. So I think that as a joke, and I remember that per conditions of the program, we were allowed certain amount of money to spend per vehicle. So if we propose a technology and it costs a certain amount per vehicle, that was acceptable. And we were kind of joking that, well, we can propose to customer to buy a warm coat for that amount of money, and that would solve the problem. But of course, that wouldn't be a possibility. Apologize if that was meant as a joke. So there is a number of issues going after that benefit. And one of the significant issues is that thermal processes are slow. So if you look at something like engine power, it changes fast. But if you look at, for example, engine coolant temperature, and you probably know from your own vehicles, that doesn't change very fast. So that means that you have to worry about processes that are developing or evolving over multiple time scales. And so that creates complication for control. And just as one example, here if we are trying to avoid battery temperature constraint violation in a battery electric vehicle, how could it happen? Well, you accelerate to high speed, and if you don't start pre-cooling, you might actually exceed that limit. And so you kind of need to start pre-cooling fairly far in advance. So if you see this acceleration coming, not far enough in advance, you may not be able to pre-cool the battery. So there's a couple of challenges of dealing with long prediction horizons. One of them is that if you try to do optimization of a long horizon, you incur high computational cost. And then the second is that to be able to predict the vehicle speed over a long horizon, that's a complicated matter. You incur very large forecast uncertainty. So we've been working on various methods to be able to predict the forecast, and I'll show this in a little bit more detail later if I have time. And also we have certain strategies how we might implement model predictive control over this longer horizons, where we combined, we call this multi-horizon MPC, where we might have what we call a short receding horizon phase, where we use better, more accurate models, and then we have a longer, what we call shrinking horizon phase, where the models may be cruder, and essentially we use this phase to form a cost to go for the receding horizon MPC, and this type of tricks are helpful. So as I have still some time, maybe let me describe some of the work that we've done along these lines, in particular for eco heating. This is for hybrid electric vehicles, so you still have an engine. An engine is used as a source of heat for the cabin here. But in a hybrid powertrain, you can also shut off the engine. And if you want to look at simple models for such a powertrain, of course, you can develop something significantly higher fidelity. But essentially, you can look at the model for the coolant temperature of the engine, which again is a source for the cabin heat. And this is essentially first law of thermodynamics, and then state of charge dynamics for the battery, as well as power balance for battery power and engine power, which add up to create traction power. Now, what is the opportunity there? So if the coolant temperature drops low, then this diminishes the source for cabin heating, and engine has to be turned on and be idling to provide heat. So that's a problem. And so what you can do as an eco heating approach is to foresee and avoid such an efficient operation through model-based prediction. So the idea is that you look at the vehicle speed here, and you know that the vehicle speed is going to go to zero, so you're going to be idling here. And the idea would be to try to increase the temperature, engine coolant temperature, before this period, so the engine can be shut off. The engine coolant temperature is going to decrease, but not going to be too low, so you're not able to provide the heat to the cabin. And so by avoiding the engine restart, you save fuel, right? Because you don't use the fuel when the engine is shut off. So it's possible to implement such functionality using MPC. I'll skip the details. They're in the papers that I'd be happy to provide. But this is some of the experimental work that we have done. We've been focusing on a very particular road segment for some of our demonstration work, which is a Plymouth Road in Ann Arbor. It's known for having multiple congestions here. And also there is multiple traffic lights along this road. Now, when we test, we don't test on the actual road. We replicate this drive on some side roads where there are no vehicles, so we don't interfere with the traffic. And so this is how Michigan looks during winter in some of the side roads, and this is our test vehicle in the process of the testing. But indeed, for this type of drives, we can realize a fuel saving of something in the order of 4.7%, which is percent savings in automotive vehicles are already significant. If you can even save 1% of fuel, that's significant in those applications. And again, this is done by this eco-heating strategy. Now, of course, you realize that the central aspect to being able to do the things like that is being able to predict the vehicle speed over sufficiently long horizon. And so that's a challenge. Road grade 2 and willpower as well, but the vehicle speed is the most difficult thing to predict because you are driving in traffic, right? And so so we've looked at a variety of ways to do this. For the short term, using some of the queuing models, in particular shockwave profile models developed in literature. They're implemented in some of our systems. We also looked at machine learning approaches, for example, using long short-term memory neural networks that we can predict the vehicle speed 10 seconds in advance. And here we are using, in addition to conventional historical data and vehicle velocity measurements, we also try to use advanced sensors, in particular radar and few others. And that even without thermal management, just at the purely power level management, that already provides some benefits, the short-term prediction of the vehicle speed. This is another idea that we explored. If you look at the vehicle driving, doing repeated drives over the same route, if you look at time domain, it's very difficult to see a pattern, as you can see here. However, if you look at the vehicle speed versus distance, and you transition to spatial domain, then the patterns in vehicle speed become more distinguishable. And so it's a very simple transformation going from time, predicting in time, predicting in space, which improves predictability. Now, for the medium-term vehicle speed forecasts, it turns out that we found very useful to use the machine learning methods, in particular neural network. And for medium-term forecasts, what we're trying to, the key component to predict is whether or not we are going to stop at the next traffic light. Because if we are going to pass through the traffic light, we have historical data, we have speed limits, and we can compose a reasonable prediction of what the vehicle speed is going to be. But difficult thing to predict, are we going to pass through the traffic light or not? And there are multiple dimensions to this problem, but assuming that the traffic lights are not adaptive, so they have sort of stationary phasing and timing, we can train neural networks that are able to predict whether we are going to pass or stop at the next traffic light, and that allows us to inform the vehicle speed forecast. For longer term, even longer term vehicle speed prediction, we've been looking at methods that involve Bayesian networks. So the idea would be to think about this scenario where you have a road with multiple traffic lights as interconnection of nodes, and red means that you stop, and then green as that means that you pass. You can create a number of scenarios, what can happen to vehicles. Some of them might get stuck, some of them might go through. And then based on historical data, you could actually estimate the probabilities or percentages of the vehicles that following each branch. And what's then is very interesting is that once you know on which branch you are in, and you look at data just limited to that branch, then there is a better predictability of what the vehicle speed profile is going to be. So the idea would then to try to predict the most likely branch that we are going to follow, and then pick a prediction of the vehicle speed profile from that branch that then we can use in optimization in model predictive control. Now, of course, we update this. For example, here, if it so happens that I was assuming that I will pass through this traffic light, but in reality I got stuck, so I'm going on this branch, then I will re-optimize for the fact that I'm on that branch and might go on this branch here. Yes. So here I think we had multiple vehicles. I would have to look it up. I can, if you send me email, I can send you the paper. So. Anyway, we've tried to do. We've tried to understand sort of what are the benefits of being to accurately predict the speed over short term, medium term, and long term, and how closely we can come to the results. And the reason you see the distributions here is because we have multiple simulated vehicles in vSim. That's a modeling package used in this type of applications. We have them going through this type of scenarios, and so we end up actually with a distribution. This is done not on real vehicles but in simulated vehicles. But essentially, the closer we are to zero, the better the results we have. And so, indeed, there is a value in doing this type of predictions the best we can. But of course, it still remains a challenging problem. Yes.
It would be straightforward that the traffic lights inform the car that how long it will stay green.
Yes. So there are. In this work, we assumed that the vehicle is automated but not connected. It's an excellent comment, and this issue of traffic light and vehicle interaction, it's very interesting because the traffic lights could be adaptive. So the traffic might inform the car that it's going to turn green or red, and that would create a different solution. But then in optimization, you need to know this information ahead of time because you actually want to travel through a stretch of traffic lights in a situation like this. And so you would have to receive information from all these traffic lights while they might adapt to whatever objectives they're doing. So I'm not saying that this is a complete solution. It's just an area that we've been recently exploring and developing various approaches to address. Yes?
You can sort of think of a next level of this where you had a dynamic optimization of the traffic flow for energy consumption with feedback between the traffic lights, the traffic conditions, the cars, and so on.
Absolutely.
Course,
you can.
This gets complex, I'm sure.
Yeah, of course, you can have kind of a green waves and those type of ideas where the traffic is optimized, it all depends on a setting, on a problem definition, and also what can be implemented.
One can also foresee that the negative impact of the system crash would be.
Well, that's one, but then, for example, if you are an automotive company, you own a vehicle and you can do something to that vehicle, but you don't know the infrastructure, at least in the US, and so it depends on coordination between. So I think the societal solution is pretty clear that you optimize at all these levels, but from perspective of, at the moment at least, from the perspective of individual manufacturer, you might say, well, I just worry about my vehicle. That's not an optimal solution. There are better approaches to do it, and in the future perhaps there will be better approaches. So. But at the moment, the problems exist at different levels where you just want to get something at the vehicle level.
You should maybe be connected to the computer of other cars because you have the traffic lights and then you have all the cars around. And if you know where to go, but then you know what the other one is doing, then it's a crash.
Absolutely. And in fact, from automation, and that's one of the things that we also emphasize, or well, not emphasize, but note in our survey, if you look at traffic consisting of all human-driven vehicles, we understand that. And if you look at the traffic consisting of all automated vehicles, so everybody coordinates with everybody, they believe that actually it's an easier problem than have a few automated vehicles driving in a traffic of human-driven vehicles. And so in a way, currently we are working actually on a harder problem than if everything would be automated. And I think you're exactly right that if all vehicles communicate with each other, you can do absolutely better job. You can better job. Again, and this goes back to discussion we had a few days ago, that from perspective of manufacturer, you have to worry about what happens if communication fails or communication is not there. So you have to worry about handling failure modes, and so the complexity of the system also gets factored in. I'm not suggesting that doing vehicle-to-vehicle communication is not the right idea. I'm just suggesting that it actually has some complexity to it as well. Nothing is easy. How I'm doing this time? Please.
Just an idea. If you have a public transportation and you are the owner of this public transportation, but you are also the owner of the red light, so you can maybe a part of the vehicles which are full connected because it's public transportation, and you can manage the whole stuff for your public transportation. I know that in Brussels there was some communication between the bus and the red light, but just for the traffic flow, not for energy consumption. But maybe there is possibilities there.
Yeah, absolutely.
Because then you own the whole infrastructure, you own the buses, the
Yeah, I think this is an excellent comment, and many of these questions, they don't exist solely in technology domain, right? There's a policy and societal domain that is as heavily baked into some of this. I'm just describing some of the things we've done. So, very quickly, looking at the cooling side and what we try to do about this air conditioning, energy consumption of the air conditioning, and some ideas we try to exploit there. So in that case, we started using a high-fidelity model called CoolSim. It's available from the national labs in the US. And then we tried to derive a control-oriented model, which just represents the cabin temperature, evaporated temperature, and air intake temperature. And those are not very complicated models from if you are in kind of a high-fidelity modeling of the systems, but that's something that we try to identify and use for control. And of course, we compare this to data from high-fidelity models as well as from vehicles as well. Now, what is an opportunity there, and where is the opportunity? So the opportunity there is that if you look at air conditioning system, and it consists of evaporator, condenser, and compressor, and basically circuits here. If you are driving at a higher speed, then the condenser efficiency increases because the RAM airflow comes at a higher speed. So this operates more efficiently. Now, there are other processes, in particular heat transfer from outside into the vehicle, and that actually gets worse, right? Because essentially you've got a heat exchanger that has a higher flow. And so how this all plays out is interesting, but overall we found that on the models that we have is that the overall cooling efficiency increases with vehicle speed. And so that happens over, so if we drive, for example, the CoolSim model at different different speeds. So the vehicle travels at different speeds, and this is versus time. Then we find that generally the efficiency is improving as we drive at a constant, as we drive at high speed. And then if we do it versus constant distance, the improvement is even bigger. And the reason for that, if you travel at high velocity, you end your journey earlier, and then you turn off the AC, so you don't lose energy that way. But that's of course obvious, right? So the faster you drive, the less energy AC uses. AC losses are fundamentally time-based. And then we've started to look at a number of ideas where we might say, well, if I have a normal cooling, what happens is that the passenger, the driver, sets a set point for the cabin temperature, and then we control to that temperature. And so if we want to do echo cooling, one of the things that we might try to do is that we might try to define some kind of a corridor for that temperature, and we could let the temperature vary a bit. With the idea is that we run the AC, we kind of cool a bit more when the vehicle velocity is higher, and when the vehicle velocity drops, for example, we idle, we let the temperature rise a bit. So that's kind of an idea. And if you're able to do it, then we can try to improve the efficiency. And so we looked at this kind of strategies for operating the AC. In fact, this echo cooling, we also combine it with echo driving, where we optimize the vehicle speed profile using the skewing dynamics at intersection models. And so we do this sequentially. We first optimize the vehicle speed profile. We then optimize the HVAC, the AC operation, and then that gives us some ideas about what our power required to drive the compressor and blower. And then the final stage is that we optimize the power split between engine and battery. Again, this is in a hybrid electric vehicle. And so over the same kind of a stretch of the Plymouth Road that we've been working on, this diagram sort of shows what we see in terms of improvements. At least for this particular drive on the models, we see that if optimized vehicle speed, we get about 11.9%, and then this benefit grows to 14.2% improvement, and all the way to 18.8% after a power split optimization. We did do vehicle tests with that system, and the vehicle looks cleaner because we do testing in the summer. Again, we do it on a side roads, we actually saw at a vehicle level, we saw about 5.7% benefit exploiting the strategies. And this is unfortunately. When I was working in automotive company, you have access to what's going on inside the vehicle. But if you buy the vehicle, then you can only do limited things. You can instrument it with sensors, and you can certainly override things like a cabin temperature set point or operation of the blower, right? But it's difficult to you can't modify the in-vehicle software. So we were kind of limited what we could do. And here, optimized. For example, vehicle speed profile, it was followed by the driver, and then the optimized cabin temperature set point, the blower operation, where we were able to control them through the laptop computer. Now, of course, it's if you come to think about thermal cabin temperature management, it's not just about the temperature, right? It's about really thermal comfort. And that combines not just the temperature, but also airflow over the body. And you could argue that, well, you have to develop a little bit, a bit more complex comfort models that are linked to temperature, but also account for other things. We've done some work in this area as well. using predictive mean vote model for occupant thermal comfort. And this type of models can also be integrated in model predictive control, and you can look at benefits that they provide, and so on and so forth. That actually brings me to the end of my my talk, and I just summarized a few closing thoughts that I wanted to leave everyone with. First, I think that automotive engineering has become as much about algorithm software as hardware. And so that's for those of us, including myself, who work in this area, that's exciting. Control has often been characterized as a hidden technology, that it's not really visible at a customer level, but that has been changing, and that's, I think, is important. There's many exciting developments exploiting vehicle connectivity, automation, information data, control software, advances in computing and artificial intelligence, and there is also many opportunities for research. Now, which of these ideas ultimately make it to real products? What I like to tell myself is that automotive engineering is about a couple of things. One of them, it's a low cost, fundamentally. The other one is a high reliability, right? You cannot have quality problems. And then development and deployment processes are very important. So essentially, whether something that works but difficult to explain, there is a difficulty in adopting this. I would say that compared to the time when I started in the automotive world, there is a high acceptance threshold for more advanced solutions. Of course, if they work, and so that's again exciting. That people are willing to try more advanced ideas and more advanced algorithmic ideas. And of course, future is yet to be written. There's many exciting developments. What's going to happen to electric vehicles? What's going to happen to automated driving? And so I think we'll see more clarity on that in the next few years. And I'll stop here.